In this lesson, we're going to talk about superposition. The idea of superposition is that if you are studying a linear system, which we just talked about in the previous lesson, we can actually look at the response of a system or determine the response of a system by considering the individual inputs one at a time. So let's consider a circuit for a moment, a simple circuit that I will redraw as a system in a moment. Okay, we're going to look at a very simple system to start out with. It has a voltage source and it has a current source and two resistors. Call it VS1, IS1, IS2. Those are the two sources. Okay, and let's go ahead and solve this, and then I'm going to show you how we can solve it with superposition. So let's say that we want to determine the voltage at this node V1 here. So what we could do is we could do nodal analysis. Right now, you know there's another node here, right? This other node, the voltage source is connected to it, and so I know from nodal analysis that I don't need to write a KCL equation there because the voltage source VS1 is going to determine what that voltage is. So I really only have one node, one unknown, one equation to write. So let's write KCL at V1. So what I have is summing currents going from left to right and currents leaving. I will have V1 minus VS1 over R1 plus the current going through R down through R2 is V1 over R2, and then we have minus IS2 leaving the node. And I simply solve. I collect the terms for V1. And put everything else onto the right side. So I have IS2, and then I have plus 1 over R1 VS1. And finally we can write V1 is equal to 1 over R plus 1 over R1 plus 1 over R2 times IS2, and then plus, and let's see, I'm going to rewrite that. You know, the 1 over the sum of the inverses of R1 and R2, if I multiply top and bottom by R1 times R2, I will actually get this, R1 times R2 over R1 plus R2. Okay, and so what I'll have for my second term is R2 over R1 plus R2 because the R1 got canceled times VS1. Okay, so not a hard problem, just one node, one equation, one unknown. Now notice the format of the response. There are two sources in this system, and there are two components to the response. The response, in this case being the voltage at V1, has a component of its voltage due to the source IS2 and part of its response due to the source VS1. And if we were going to consider any other voltage or current in the circuit, we don't have too many choices here really. We could talk about the current through R1 or through R2. We would find that likewise, if you were to express either of those currents, you would find a solution where they would involve a term that is a coefficient, a constant times IS2 plus a constant times VS1. Okay, once you've picked the component values, R1 and R2, those will just be numbers, coefficients out in front of IS2 and IS1, IS2 and VS1. So, although I'm not going to prove anything here, I'm going to say that from this we see, or this example demonstrates that all responses in a linear system are expressed as a weighted sum of the sources driving the system, or supplying the system. Okay, that may sound like some funny language, but let me abstract from the circuit again and say I've got a system T. And instead of having just X going in, one X and an output Y, I actually in this case have two inputs. I'm going to say I have an input IS2 and I have an input VS1 and I have an output or a response V1. Now you might complain, wait, how can you call those inputs? There's no input to the circuit, there's just a circuit with two sources. Okay, and what we mean by input is if we were to take out, okay, the first question is a voltage source, is a voltage source or a current source linear according to the definition of linearity? Right? You think of a voltage source, if you have two things, you have voltage, you have current. Is there a proportional relationship between voltage and current for a voltage source like there is for a resistor? No, there is not. And neither is there one for a current source. Right? And if you look at a voltage source, if I apply some current here and I have a voltage on the vertical, that is my voltage source. Right? And here is my current source. Okay, neither one of those show a response that is a straight line passing through the origin, which is what must happen. There cannot be any offset. So from this, we would say, therefore, V source and I source are not actually linear. And you might say, wait, I thought you said that we're going to study linear circuits and all we know about are resistors and voltage and current sources. You're now saying voltage and current sources are not linear. Well, actually, the way we treat voltage and current sources is that we treat them not as part of the system. They're actually outside of the system, and they are what's like stimulating the system. Okay? They're what's moving. They're the prime mover behind the system. Or if you will, what you've heard the term network. Okay? You think of what remains after you take out the sources is this network that you now are going to stimulate with your energy sources, a voltage and current source. So once you take the voltage and current sources out the independent ones out of your circuit, what you're left with is a linear system. And here we call it T. But now that system has two inputs. It has an input IS2, the current that is pushed or provided, supplied by S2, and you have VS1, the voltage supplied by source VS1. And if you will indulge me and accept that, then in an abstract way here we can write that such a system, T, would have a response V1 that is actually awaiting, I'll just call it K1 IS2 plus K2 VS1, right? Where K1 is just this ratio of resistances, and this K2 is a ratio of resistances. And the beautiful thing about this, maybe beautiful is strong, but in a geeky way, nerdy way I should say, it's beautiful, and that is that you can find the total response in the total response of the system to these inputs by considering each one of them one at a time. Okay? And that leads us to this idea of superposition. The response for a linear system, I should write this. For a linear system, the net response, or the response, is a superposition of the individual responses. In other words, the responses due to each independent source acting alone. In other words, it's the only one that's on. So we're going to go back to this circuit and we're going to solve it using superposition. So what we will do is we're going to decompose this into two circuits. So use superposition to solve for V1. So in one case, we're going to turn off VS1. In the other case, we're going to turn off VS2. So first, we'll redraw the circuit with VS1 and VS2 turned off. I'm sorry, IS2. And one of the gotchas initially for students learning this is, what does it mean to turn off a voltage source? Well, if I dial down the voltage of VS1 to 0, then that means the voltage across here goes to 0. If that voltage goes to 0, it means that this node up here is actually now at the same potential as the ground node. In other words, it's shorted. Okay? So this is i.e. when you turn off a voltage source, i.e. short the source. It's not that you're shorting the source. The source is a short circuit when it goes to 0 volts. And similarly, when you turn off a current source, the current here goes to 0. And when you turn off a current source and there's a 0 current flow, then that means that's equivalent to if there was no path at all. So turning off IS2 is, you say, in other words, you open a current source. And again, you don't really open it, it's just that the current source becomes an open if you set its current value to 0. So now we redraw this with the source off. And then with, that's with the voltage source off, and then we'll redraw it with the current source off. And we'll call the node V1. In one case, we'll call it V1 prime, and then we'll call it V1 double prime. And what what superposition says is that V1 will be equal to the superposition of the two individual responses. And this we can solve by inspection. First, we have V1 for V1 prime is just equal to, if you look at those two resistors, they are in parallel. So it's just I times R. And V2 or V1 double prime is now just the voltage due to voltage division of VS1 across R1 and R2. And so that's going to be, by inspection, the voltage across R2, which is R2 over R1 plus R2 times VS1. And we put these two together to arrive at V1 is equal to R1, R2 over R1 plus R2 times IS2 plus R2 over R1 plus R2 times VS1. And this answer is exactly the same as what we found previously. So to recap, when we're studying linear systems, which is all that we'll do in this class essentially, you can use superposition to help you solve problems. Sometimes it will help you significantly, other times it will not. In this case, it wasn't that hard to do it, write the 1 KCL equation. But here, you could get it with superposition, you could get it simplified enough that you could just write things by inspection. So again, in summary, superposition says that you can find the total response to the system. This means any voltage or current in the system by just considering the response of the system to each individual independent source acting alone, and then you add all of those up, those responses together to get the net response.